Good afternoon, everyone. My name is Samaneh Seifollahi, and I'm a researcher at the Department of Physical Geography. And today I will talk about systems thinking approach for integrated understanding of land-sea interactions in the Baltic region. And in this work, I have been collaborating with Zara Kalantari and Georgia Destoni from the same department. So we know that Baltic Sea is suffering from eutrophication and water quality issues. And if you look at the map, it shows that around 96-97% of the surface area of the Baltic Sea is actually showing the poor water quality condition when in comparison with the Water Framework Directive measures. And that, as has been discussed in previous presentations, that's because of the excess nutrient input, nitrogen and phosphorus, and that's not just the active input, it's also based on the historical input that has been in place, and it has been accumulated and stored in the soil, sediment, and slow-moving groundwater, and now is actively contributing to the waterborne nutrient input to the sea. And if we look at if we take a closer look to one key catchment in this, in the Baltic Sea coast, and that's the Nordstrom drainage basin, a Swedish coastal area. If you look at the plot, there has been a significant reduction in nutrient input to the sea, but at the same time, we see that the level of phosphorus input has been kept in a constant level. And that means that even though we have put in place so many regulations, environmental policies, and there has been a lot of actions that are taken so far with different sectors, we have been able to reduce the active nutrient input, but at the same time, we haven't been able to sufficiently address the reduction of legacy sources and their contribution. And that's why we are still above the targets set in the Water Framework Directive and also so many other regional policies like the Baltic Sea Action Plan. As I said, the Baltic Sea Action Plan, which was developed in 2007, it was also updated based on the status of the water quality in the Baltic Sea in 2013, and it's still being updated in 2021. It addresses four main aspects of the problem, and that's eutrophication, of course, reduction of the nutrient input, biodiversity restoration and development. It addresses hazardous substances reduction and also maritime activities. But it hasn't been able to address the complexity of the interactions and involvement of different human activities with so many pressures that are happening in the region, and they are actually contributing to the poor water quality in this region. This is one aspect. Another aspect is that, of course, Baltic Sea is a kind of shared resource among different countries, and we shouldn't ignore the impact of other coastal areas, other catchments around this basin, the whole basin, and also the interactions and feedbacks that we get from other regions. So regardless of what action we take at the local scale, we need to also take into account what impact other regions would have or other policies and regulations would have in our region. My research is part of an EU Horizon 2020 project, and it's called Collaborative Land Sea Integration Platform, shortly COASTAL. And in this project, we are not only looking at the Baltic Sea, but we also look at 5 other coastal areas in different European countries, and we are collaborating with 29 European partners, and they are from different sectors. So we have consultancy, we have industrial sectors, we have tourism, and so on. And the framework, the workflow that we have followed in all these case areas has been involving from the beginning stakeholders, different actors who are actually contributing to the problem and who are being affected by the problem. And to get their perspective, incorporate those perspectives in our system dynamics modeling, support that modeling by data and other kind of systematic models that can be fed into our system dynamics modeling, and then test the effectiveness of different business solutions and also policy regulations, and then get feedback from the same stakeholders. So stakeholders, different actors have been involved from the beginning in the project and have been with us through the whole steps. So we have been able to collaborate with them closely and get their feedback and see and make sure if their perspectives has been enough reflected in our modeling, because as you all know, it's really difficult when it comes to citizen science and combining those qualitative knowledge with our quantitative and modeling knowledge. Looking at the Baltic case, which we focused on in this coastal project, we are looking at the Nordstrom drainage basin and its coastal areas of the Baltic Sea. And we are dealing with two types of water-related problems, of course, water quantity and quality. And when it comes to water quantity, we have too much water here most of the year, but at the same time, the projections, the hydroclimatic changes show that we will have need for irrigation, and there is a lack of facility and investment in that regard. But we are also dealing with excess stormwater and the capacity for handling that and the wastewater treatment, and of course the impact of climate change. But all these water quantity aspects, they also contribute to water quality problems that we are dealing with, not only on inland waters, but also the coastal and marine water. And that's what's going on in all small coastal catchments and drainage basins around the Baltic Sea. And they affect different economic activities such as coastal tourism and recreation, which is already growing on in this region. Yeah, as I said, we started with a stakeholder engagement, and for that we had 6 thematic stakeholder workshops, and in each of them we invited relevant stakeholders from local and local and regional stakeholders, and we just discussed with them how they know the problem and what are the main components of that problem and how they are being affected with the problem. So this is what we draw in different workshops, and we summarized the outcomes of the discussions, of course, with the stakeholders at the same room, in kind of mind maps. And in these mind maps, we included all the system components that different stakeholders discussed and the interactions that they have with each other. As you see, the complexity of the interaction between human activities and all the pressures, water quantity, water quality issues is already clearly reflected in these graphs. And then, of course, that's really difficult to transfer those graphs into system dynamics modeling. That's why we simplified them with, again, together with the stakeholders. We replaced some of the variables, we combined some of them, and we replaced some of them with some quantifiable variables, because of course we had some qualitative variables there as well. And then we try to combine those mind maps to get develop a unified and simplified causal loop diagram, which shows the causality between different components, and also it clearly showed us the main interactions and feedback loops, the direct and indirect interactions that are involved in the system. And of course, we categorize those components just to have an overview of different problem aspects. Again, if you look at this diagram, it's really difficult to model each and every one of these interactions and to quantify all these components. So what we were still dealing with a big challenge of complexity in this system. And we wanted, and that complexity comes from nonlinearity, which is kind of the nature of all the interactions in this system. And of course, all the feedbacks, because it's really difficult to quantify those feedbacks, all the impacts that we receive from different drivers around the region, and those are not basically local drivers. This shows different steps that we took to transfer that unified and simplified causal loop diagram into a systems dynamic model. And that's how we use different quantitative data sources. We also used other mechanistic models that were going on in our department in parallel with our projects, and all of them they feed into our system dynamics model. And when we developed the system dynamic model, again, another challenge that came up was how to communicate the outcomes of our model with policymakers and decision makers, because we already know that, okay, there are different actors who are contributing and they have already cut down their loads to the Baltic Sea. For our system dynamics modeling, we had two parts of our model. One was focusing mainly on water quantity, and another one was focusing on water quality. And that's why we call them land-sea, intersectoral, and coastal water and waterborne nutrient exchange model. And this is a dashboard, a very simplified dashboard that you see it here. It's really difficult to show all different views of our model. So I decided to show a very simple dashboard, and the user can play with the indicators and also different variables and different scenarios that there is a description for them in the model, and see how different graphs would change in relation to water quantity and water quality. And when it comes to water quantity, we are addressing different sectors like green sector, we are addressing urbanization, tourism, and also natural water flow, and so on. And this is one simple change in the graphs that you see if we make any change. So what we wanted to check and use our model for was actually to test different changes and see what will happen to water quantity and water quality and how we can improve the problems. So we looked at the green sector and urbanization and tourism, and of course they are happening together, their development in our region. So we look at their impacts, the combined impacts of them, and at the same time we have the impacts of hydroclimatic changes and different policies that have been in place so far, or the new ones that will come up based on the projected developments. And we aligned our scenarios and different changes with different RCPs and SSPs in our region, and we downscaled them to our local area to see how different changes can be quantified in our model. As a really initial result, sorry because of the typo in the on top of the slide, that's not economic sector on top, it's hydroclimatic components. We can conclude that when it comes to local scale, of course, the local actions can improve our inland and the corresponding coastal water quality. But if we want to look at the broader perspective of the whole Baltic Sea, we need to also look at regional actions. And those regional actions, they need support, they need financial support, they need policy support. And that's not happening, and that will not happen. Water quality improvement will not happen if we only look at a specific sector. So we would need cross-sectoral collaboration. We would need cross-regional collaboration to improve water quantity. And at the same time, we need to consider the historical impacts of anthropogenic activities in the region, not just the active part. What we are going to do in the next step is to develop different business roadmaps and policy solutions based on the outcomes of our model, and to communicate them with relevant decision makers and policy makers in our region who have been involved from the beginning in the project as our stakeholders. This is the webpage of our project, so please go and check for more information. And the small image here shows the logos of different partners. And you can, of course, we are happy to answer your questions, and you can reach out to us for further information. Thank you.